Hello, everyone. I'm Jingyu and come from the Institute of Mechanics, Chinese Academy of Science. It's my pleasure to present our current work in the conference. The title of my talk is Fatigue Crack Propagation at Whole Ages on Nickel-based single crystal alloys under thermomechanical loading. At the very beginning, there is a short introduction of the background. Many studies show that the crack of the turbine blade often initiates at the film cooling holes, since the stress concentration occurs around the film cooling holes. And this figure shows a typical aero engine. If we look at the turbine blade, it's made of the nickel-based single crystal alloy. In order to reduce the temperature of the material, the cooling air was passed through the internal channel and then come out from the film cooling hose. If we consider a takeoff and a landing process of the plane, the temperature and mechanical loading vary simultaneously. There is a typically failure mode of the thermomechanical fatigue. The material investigated in the present work is the nickel-based single crystal alloy, DD6, in Chinese series. And the original material is a kind of cast rod. We should keep in mind that the actual direction of the rod is just the crystal direction in 001. And the chemical composition of DD6 alloy is listed in the table, and heat treatments of the rod were as following. And the right-hand side, this figure shows the microstructure of the DD6 alloy. It contains two phases. One is gamma and the other one is gamma prime. The average size of the gamma prime phase is about 0.6 micron. Okay, then all specimens was manufactured from cast rod. Also, the actual direction of the specimen is just in the 001 direction. And the solid specimen are used for the isothermal fatigue test, and the tubular specimen is just used for the TMF test. And for the tubular specimen, we have three different cross sections. The first one is a smooth one, and the second one, we create a film hole in the 010 direction. And the third one is just we take the hole in the 011 direction. We use the so-called picosecond laser method to create the film hole. And of course, there is a remelt layer about 2 microns. Then we develop a test rig for the TMF test. Based on the very beginning, we have the fatigue test frame, and we add induction heating to heat the specimen. And also we use compressed air to cool down the specimen. And because we want to detect the crack near the hole, therefore we use a scope to monitor during the test. We have three different kind of loading conditions. The first one is IF, is called isothermal fatigue. The second one is in-phase thermomechanical fatigue. And third one is out-of-phase, we call it OP. All the tests are controlled by the mechanical strain, which can be calculated from the total strain minus the thermal strain. Of course, the thermal stability is very important. Therefore, I use 3 thermocouples in the gauge length of the specimen, which at the top, middle, and the bottom. We have to reduce the temperature gradient in the gauge length. And the stress ratio, the mechanical strain ratio is -1. And the temperature range is from 400 degrees to 980 degrees centigrade. Okay, that is the loading condition of our experiments. And the next step is we have to observe the crack near which initiated from the film hole, it's really a challenge because the hole is very small and surface temperature is very high. We have to use a blue light source to ignore because when the temperature is very high, the specimen itself is radiation, the red light outside. Therefore, we use a filter to ignore all the red light, just detect the reflect blue light. And a telephoto microscope was used to detect the small area around the film hole. Of course, because there is a lot of I think so-called turbulence, air turbulence. So therefore, we have a lot of noise of this figure. Right now, it cannot be ignored, right? Okay, that is the overview of the experimental results, the fatigue lifetime. And in this figure, the black mark, which is the isothermal fatigue state, the red one is in phase, and the blue one is out of phase. It can be seen that the thermomechanical fatigue life is much smaller than the isothermal fatigue one, and the OP is dangerous than IP. Of course, it's interesting. The direction of the film hole also influenced the fatigue life. 011 is less than 010. This page shows the fracture surface of the specimen. It can be seen that the crack initiated from the hole edge, and for the OP case, in-phase case, a thick oxide layer is observed at both on the hole surface, also on the crack surface. And for the out-of-phase condition, a very clear crack striation was found. And before the final fracture, I just take off the specimen and polish the specimen in the actual direction. And we use EDS to observe the oxide regions. It can be found that the geometry of the oxide region is very different for the IP and OP conditions. The oxidation area of IP is much larger than that of OP. Okay, let's zoom the figure and focus on the crack tip. It can be seen that the geometry of the oxide region is determined by the thermomechanical phase and the crack propagation rate. The crack propagation and oxidation are coupled with each other. It can be seen, I think, we can imagine that the oxidation speed is dependent on the diffusion coefficient, the temperature, the stress, also the crack propagation rate. And the crack propagation rate is dependent on, for example, the amplitude of the stress intensity at the local temperature. Also, they are coupled with each other. It can imagine that for the OP case, when the crack is opened, it related to the lowest temperature, but for the IP case, the crack opened related with the highest temperature. That is why the in-phase oxidation area is much larger than the OP one. It can be seen that these two different velocity relation is very important. If the oxidation faster than the velocity of the crack, it can be seen that the crack was around just tripped by the oxidation area. Then the failure mechanism is totally different. Therefore, the fatigue life is really different. Okay, right now we want to measure the crack propagation rate. You can see that for each test, I just take more than 10,000 figures, and a package is so-called OpenCV. It's used to pre-process these figures. And we have to find the figures at the moment of maximum tensile stresses. It means at the most tensile stresses, the crack is the most clearly to detect. And right now we have the crack length versus the loading cycles. And with this figure, we can also calculate the dA over dN versus delta K. It can be seen very clearly. The crack propagation rate of this blue one's OP is much higher than the IP conditions. Also, the crack propagation rate at the whole edge with direction of 011 is higher than that of 010. Okay, that's all of the experimental results. We tried to do some computational results. The first, because the whole material is a single crystal, therefore we have to use the crystal plasticity theory. This figure just shows the fundamental formula of the crystal plasticity, which include the velocity gradient, stress-strain relation, shaft strain rate, and backstress and resistance stress. There is nothing new, but we need the framework of the theory. During the thermomechanical fatigue loading, the microstructure of the material will evaluated. Therefore, we use a dimensionless vector C to describe the evolution of the microstructure, and then connect this factor with the resistance stress, and then we can include the microstructure evolution in the crystal plasticity framework. And with the finite element model, we obtain the stress distribution around the whole edge. It can be found that actually the actual stress at the whole edge with direction of 011 is really higher than that of 010. So I think this is the main reason which why the 011 have the lowest fatigue life. And right now we try to build a numerical framework to describe the complex crack propagation behavior of the thermomechanical fatigue. So I think we have 4 different fields. The first one is displacement. The second one, I choose the phase field damage, and the third one is temperature. The last one is the concentration of oxygen. We can write each field, we can take the government equation. Of course, we have the boundary condition and initial condition. And for the displacement field, we have to consider the critical plasticity. And the benefit of the phase field method is that it will introduce it will ignore the discontinuous of the crack, and then we can combine the plastic energy as the driving force of this field to describe the crack. And finally, this crack is a kind of boundary of the concentration revolution. We think this is the internal source which dependent on the phase field phi. So this kind of distribution of the oxygen. This work is not really completed right now. I think we will publish the numerical result in the next maybe the next half a year, I think. So finally, the conclusions. The first one is under the temperature range of 400 to 890 degrees centigrade, the fatigue life of out-of-phase TMF is the shortest. And the second one is competition between crack extension and oxidation process plays an important role in the TMF crack propagation. The last one is fatigue life of hole at 011 is lower than that of 010. Yeah, that's all. Thanks.